So welcome to the another annexure lecture of the course Fundamentals of Additive Manufacturing Technologies. In this annexure lecture, we shall discuss today about the omnidirectionality in additive manufacturing systems. So this topic is important to learn about additive manufacturing because this particular phenomena usually observed in almost all the additive manufacturing processes. And in the end of this lecture, you will have the answer of why such a sophisticated system is used in DED, where there is a laser coming from the center and the powder is delivered through a conical nozzle. While the system, when it was first invented by Professor William Steen, it looks something like this. It was very simple system having a laser at the center, creating a melt pool, and in that melt pool we are feeding the powder which is carried by an organ gas. It is such a simple system, then why there was a need of converting this very simple system to such a sophisticated system? And the answer is omnidirectionality of the process. So let us discuss about this in this lecture in detail. This is going to be the content for today's lecture. We shall discuss briefly about the introduction of additive manufacturing, the different processes by ASTM, and then we shall rearrange them based on omnidirectionality. And then we shall discuss about the omnidirectional additive manufacturing system. We'll try to give a proper definition of the same. We shall discuss the inherently omnidirectional additive manufacturing systems. And then we shall discuss in detail about the omnidirectionalities in all 7 processes of additive manufacturing defined by ASTM, like omnidirectionality in direct regenerative deposition, omnidirectionality in material extrusion, omnidirectionality in wet photopolymerization, omnidirectionality in sheet lamination, powder bed fusion, material jetting, binder jetting, and then in the end we shall conclude our presentation. So we all know that the additive manufacturing processes have been classified into 7 categories by ASTM, as you are seeing on this slide. We have already discussed about it in detail in the first lecture of the module 1, where the additive manufacturing processes are grouped in 7 technologies. The first is called as wet photopolymerization, second is material jetting, third is binder jetting, fourth is material extrusion, fifth is sheet lamination, sixth is powder bed fusion, and seventh is direct energy deposition. So why ASTM has aligned these processes starting from wet photopolymerization and ending with DED? It is based on the energy consumption required in the process. So we start with wet photopolymerization, and with DED, like I already mentioned, the energy consumption is very high in the case of DED and it is very low in the case of wet photopolymerization. I already gave this example. Typically a laser of 40 milliwatt is used in wet photopolymerization to start the curing process, while in direct energy deposition you have to create a localized melt pool in a very big substrate, and hence to overcome the losses like conductivity, convection and radiation losses, and to sustain that melt pool in a large substrate, you require high energy source, and these source can go up to a few kilowatt, like the laser source in the case of DED may be up to 10 kilowatt also. So the energy consumption is quite high in the case of DED, while it is very low in the wet photopolymerization. That is why it is aligned like this, and it is in increasing order from left to right. Now in today's discussion, before starting it in detail, we will rearrange these additive manufacturing processes based on the omnidirectionality in the process. So like for example, the DED based processes, all the processes usually falls in the category of DED, are non-omnidirectional in nature and required a lot of arrangements to make the process omnidirectional. Similarly, the material extrusion is now number 2, then powder bed fusion is on number 3, and similarly if we go on the right side and if you look at the binder jetting, material jetting, they are inherently omnidirectional and no additional arrangements are really required to make these processes omnidirectional. So we just rearrange it so that it will be easy for us in further discussion, that when we are going to discuss DED first, because DED based processes are mostly not omnidirectional. in nature, and some arrangements has to be provided to make them omnidirectional. So let us first discuss about the definition of omnidirectionality. So the term omnidirectionality indicates an equal sensitivity of the process in all the directions. In the context of additive manufacturing, omnidirectionality implies invariance of material and geometric properties regardless of the travel direction. Omnidirectionality, more often than not, is a property of the setup. It is a property of the additive manufacturing machine or 3D printer. However, a few additive manufacturing processes are inherently omnidirectional, while others are made so by appropriate arrangements associated with it. I'll just give you the example of omnidirectionality in other processes as well here. Like this is an omnidirectional antenna which can receive the signals from all the sides. Similarly, this is a directional antenna. It can receive signals only from one side, and that is why it has to be properly aligned so that it can receive the signal coming from one direction. Similarly, this is an omnidirectional mic which can receive the voice from all the directions, while this is a directional mic which will preferably receive the voice coming from only one direction and consider or block the other voices coming from other directions. This is an example of omnidirectional wheel. Like this one is an omnidirectional wheel, and it can move in any direction, right? You can apply force in this direction, it will start moving here. It will apply force in this direction, it will move in this direction. So this is an omnidirectional wheel. While this is a directional wheel, it can roll and it can move only in one direction. Now if you want to move it in another direction, you have to provide some additional arrangements, and that is why the steering and other things are coming into picture. So the point is, those additional arrangements are required to make this directional wheel omnidirectional. But as alone, this is a directional wheel. It can only roll in one direction and move in only one direction. So these are some examples of omnidirectionality in other processes. Now you might be getting confused with the term omnidirectionality versus isotropy. So I will try to make at this point of time distinction between the isotropy and omnidirectionality. Isotropy underlies the uniformity in the part properties irrespective of the part orientation and location of measurement. Omnidirectionality, on the other hand, is associated with the machine tool. An omnidirectional additive manufacturing platform promotes the fabrication of isotropic parts. Conversely, anisotropy, which signifies the non-uniformity in the part properties, can arise from several other factors also, not only from the additive manufacturing setup. It comes from the inherent nature of fabricating the part in a layer by layer manner, and it also comes due to the thermal gradient. Sometimes it comes due to the solidification rate. There are many factors which makes the part anisotropy. But a machine tool which is not omnidirectional can be one of the major factors to produce the anisotropic parts. However, like I already mentioned, a non-omnidirectional deposition, which is often neglected, significantly contributes to the anisotropy of a part. Also, notice the definition of omnidirectionality as presented here is confined to the plane of deposition only. Unlike the isotropy is measured, the property is measured in all three directions. So while further discussion about the omnidirectionality, we shall keep these points in mind and always focus that the omnidirectionality is a property of the machine tool. It is a property of the setup. It is a property of the 3D printer, not the parts produced by it. The parts produced, if they are having such issues, or they are having the variant material properties in different direction, are called as isotropic or anisotropic parts. So now let us try to understand the importance of omnidirectionality in additive manufacturing systems. What I'll show you here is a TIG welding process in which there is a tungsten which creates arc, and that arc creates a melt pool, and in that melt pool a wire is fed from the side. Now if this is the conventional way of depositing the material and we are layer by layer fabricating the part, then the process will not be omnidirectional. What will happen in that case? In that case, three major issues may arise. Those are shown here. The first one is you have set the parameter perfectly suitable for the front feeding condition. So while moving from point A in this diagram, so while moving from point A to point B, the wire is fed from the front side and your parameters are perfect. But when it moves from B to C, the feeding mechanism will become side feeding, and it becomes back feeding when it moves from C to D. And similarly, when it comes again to D to A, it becomes side feeding. So the parameter those were suitable for front feeding, the angle, feeding angle and the height may not be suitable for back feeding. And it has been observed that the parts produced or the track deposited during front feeding will be good in deposition, but the portion of the track or the portion of the layer deposited by the back feeding may have the issues such as serrations. So serrations are nothing but the solid wire is digging the soft immediately deposited material and making a dig into it. Another issue which usually occur is, for example, your wire is not exactly getting melted at the center. Due to that, your deposition path will be, as you are seeing here in the blue color, but the deposited bead will be offsetted to it. It will not be exactly at the center. The third issue which we face particularly in this TIG based system or the DD based system is when you feed wire from one side, some portion of the arc or some portion of the energy of the arc will be consumed by the wire itself. Therefore, less energy will be reached towards the substrate. As a result, the penetration in the substrate will be less on the side where the wire was fed, and it will be more on another side where there was no wire. As a result, you usually get the beads which look something like that. You have lack of fusion where the wire is getting fed and high penetration on the side where wire is not getting fed. So these issues are mainly because of the non-omnidirectionality of the additive manufacturing setup. As you see in this video as well, when the wire is fed into the arc created by the tungsten, it becomes sometimes front feeding, now it is side feeding, and then again it will become back feeding, and again now it will become side feeding, and after some time it will become front feeding again. So the feeding mechanism itself is changing. Now if you are moving on a non-linear trajectory like you are seeing here, like circle or some other non-linear trajectories, you will not get the deposited bead consistent in the metallurgically or geometrically. Its properties may vary, its height and width may vary, its deposited material properties may vary from one position to another position. Therefore, our system has to be omnidirectional. So we need to first define this omnidirectionality in a proper mathematical way so that we can refer it for different additive manufacturing systems. So the directional sensitivity in additive manufacturing processes arises from the inconsistency between the three spatial orientation vectors relative to each other. And what are those vectors? Those are the vector corresponding to the source of fusion energy, and that is defined here as by Vs. The direction of feedstock delivery, and that is defined here by Vf, and the travel direction, which is defined here by Vd. So these three vectors are termed as, in our further discussion, as orientation vectors. An additive manufacturing system will be called as omnidirectional if and only if the relative position between Vs, Vf and Vd remains consistent throughout the process. If it changes at any point of time, then the system, the additive manufacturing system, cannot be called as an omnidirectional system. And as a result, I already mentioned, the parts produced may not be of having the same metallurgical or geometrical properties at different locations. Therefore, you have to make your additive manufacturing system omnidirectional in such cases by providing some additional features to it. So let me just show you. This is a particular example of MIG welding based wire arc additive manufacturing. Here you can see the vector Vs, which is corresponding to the source of fusion, and Vf is the vector corresponding to the wire feedstock direction. We know that in the case of MIG welding, the Vs and Vf will remain collinear. It is because the wire which is coming itself will create the arc. Hence, the vector corresponding to the material feed and the vector corresponding to the energy source will be in line with each other, or they will be collinear. And then you are moving along a path, it is called VD, anywhere onto the deposited bed. Now, if the position between Vs, Vf and Vd is always consistent, if it is a MIG welding, then definitely process will remain omnidirectional. But it may not remain consistent in some cases. Like, consider the case in which, as you are seeing here in this diagram, the wire is fed separately and the arc is created separately, like in the case of TIG welding. In that case, the TIG welding tungsten is creating the arc, and in that arc we are feeding the wire from side. Now in that case, there will be an angle between the vector Vs. Vs is corresponding to the source of fusion, and Vf is corresponding to the direction of material feed, and this angle is represented here by theta. And now you are moving in a direction which is shown here by Vd. It can be noticed now that if my deposition direction is somehow changed, like for example, instead of going in that direction, I am moving now in this direction. So what will happen? The angle between Vf and Vd, which was supposed to be assume that it is phi earlier, will no longer remain phi. It will change. And as per our definition, in that case, the process will not remain omnidirectional, because the relative position between Vs, Vf and Vd is not consistent throughout the process, or while depositing, or while adding the material in any direction. Another example let us consider of powder bed fusion, in which there is no motion is given to the powder feed delivery stroke. It is just lying there and hence having zero velocity. Correspondingly, the Vf will remain 0. Now the fusion source is coming vertically from the top, and then you are moving this energy beam, or you are depositing in some direction, and that direction is represented by Vd here. The process will remain omnidirectional if the angle between Vs and Vd is always 90 degree. But if it is not consistent, if this angle between Vs and Vd is not consistent at any point of time, then the process will not remain omnidirectional. Let us see the case as you are seeing here in this diagram, where if there is a laser source and it is projecting the laser beam on the powder bed at an angle, in that case the angle between Vd and Vs may not remain same as it was shown here in this diagram. Therefore, in such cases you need to provide some additional arrangements to make the process omnidirectional again. So let us now define mathematically which process should be called as inherently omnidirectional and which should not be called as inherently omnidirectional. So based on our observation, it has been found that if the vector corresponding to the source of fusion Vs is parallel or collinear to the vector corresponding to the feedstock material Vf, and the direction in which we are depositing the material, or Vd, represented here by Vd vector, is always perpendicular to Vf and always perpendicular to Vs throughout the process, then only the process will be omnidirectional. Otherwise, it will not be omnidirectional. So with this definition, let us move to each and every process, and we shall discuss in detail whether the process is omnidirectional or not omnidirectional. And if it is not omnidirectional, then what are the arrangements people use to make the process omnidirectional. So you will be surprised to know that we are not going to see any new arrangement today. All of these arrangements are already there in all the additive manufacturing systems. but we are trying to give a proper definition to these systems, and we are trying to explain why it is actually required and what it should be called in future if you are designing your own additive manufacturing system. So omnidirectionality in DED. So let us first check for the inherent omnidirectionality nature in the case of DED. So for the directly generated deposition based additive manufacturing process, the feedstock is fed instantaneously along the vector VF into the molten pool created by a fusion source, which is given by the direction VS, and then we move along in a XY plane in the direction vector given by VD. Like in the case of metal inert gas welding, the feedstock enters the molten pool coaxially, right? So in that case, the direction of the fusion source, that is VS, will be parallel to VF, and VF is the direction of the material feed. So the wire and the source both will be always collinear. Now we also know that the welding gun will be perpendicular to the substrate, and hence in that case VS will be always collinear or parallel to VF, and the direction of travel will be always perpendicular to the wire and the fusion source. And if you recall, if this condition is satisfied, then definitely the process is inherently omnidirectional. However, in the case of tungsten inert gas welding, plasma welding, or laser welding, or electron welding based additive manufacturing processes, the process is not really inherently omnidirectional, because in that case the direction between VF, the wire feed direction, and the deposition direction may vary, and the variation comes between the angle of the wire feed and the travel direction, and that is why the processes are usually not inherently omnidirectional. They have to make by some arrangement an omnidirectional process. So this is the schematic diagram of TIG and MIG so that you can understand these vectors appropriately. So the wire is represented here in the black color, and it is creating the arc. Hence we can clearly see the direction of the wire feed rate is represented here by a red color vector. VF is collinear with the vector VS, which is represented here in green color and corresponding to the direction of the fusion source. They both are collinear, hence VS is parallel to VF, and VS and VF both will remain always perpendicular to substrate, as well as they will be always perpendicular to the direction VD. Now you move in any direction, example, you are moving in this direction, then again the angle between VS and VD or VF and VD will be always 90 degree. That is why the MIG based or the MIG cladding based additive manufacturing processes are inherently omnidirectional. But in the case of TIG welding based process, this is the tungsten shown here in the black color creating the arc, and hence the direction of the fusion source is vertical, shown here in the green color. Correspondingly, the direction of the wire feed, which is in this case is fed from side like here, is represented by VF, which is in red color. Now if we move in any direction, for example in the XY plane, and the direction vector is represented by VD, the angle between VF and VD may not remain consistent. Maybe the angle between VS and VD is always 90 degree because our gun may remain vertical, but the angle between VF and VD may not remain consistent. You can easily assume that I am, instead of moving in this direction, moving the torch in opposite to this direction. In that case, the angle between VF and VD will change, and if it is theta, then the angle will become 180 minus theta. And of course, as this angle is changing, definitely the orientation vectors VF and VD are not consistent corresponding to each other, and that is why the process is not inherently omnidirectional. So to make these processes omnidirectional, three particular methods. So to achieve the omnidirectionality in such additive manufacturing processes, particularly for DED based processes, four methods are typically identified. The first is called coaxial feedstock and fusion source. So somehow if we have our wire feedstock or material feedstock parallel to the fusion source and then they both are perpendicular to VD, direction of the travel, then definitely these three orientation vectors will be consistent throughout the process and process will become omnidirectional. Other than that, assume this scenario in which the fusion source is vertical and coming at the center, but the feed stroke is represented not by a single vector or a single line, but it is in the form of cone and it is coming from all the sides, meaning the raw material is coming from all the sides surrounding the fusion source, and that is why this method is called coaxial fusion. That is why this method is called coaxial fusion source surrounded by the feed stroke. The top view of the same will look something like this. So VF is now not only a single vector but multiple vectors coming from multiple sides, and your fusion vector is perpendicular, and this is the VD corresponding to the direction of travel. Now you assume any direction. Assume that now instead of moving in the given direction, we are moving in this particular direction. In that case also, the angle between VF, VS and VD will remain consistent because the conical shape will be symmetrical all around the center of the axis, and that is why the process will become omnidirectional. This method, like I already mentioned, is called coaxial fusion source surrounded by feed stroke. The third method is coaxial feed stroke and surrounded by fusion source. In that case, the VF vector or the vector corresponding to the material feed will be at the center and it will be surrounded by the fusion source in the form of a cone. In that case, definitely the angle between VD, VF and VS will remain consistent now if you move in any direction because the process has become symmetrical. The fourth method could be the most simplest one, that the issue was between the angle between VF and VD. Hence, if you are moving on a nonlinear trajectory and if the direction of VD is changing, dynamically we can change the direction of wire feed stroke or the powder feed stroke or the material feed stroke accordingly in such a way that this angle between VD and VF can remain consistent. And this particular method is called as dynamically adjusting orientation vectors. So if you are moving to another position now, the VD is changing, and as the VD is changing now, VF was earlier here, but to maintain the angle between VD and VF consistent, this VF will definitely change its position dynamically and maintain the angle theta throughout, so that the angle between VF, VS and VD can remain consistent. So the method 2, 3 and 4 can be implemented for TIG or plasma based DED. So let us discuss about the DED system which utilizes TIG or plasma cladding. Let us try to implement the method 2. Method 2 says, in this case, the coaxial should be the fusion source and it should be surrounded by the feed stroke. So as you see in this schematic, there is a tungsten which is at the center and creating the arc. Now surrounding this in the form of cone, the wire should come. But we know that wire cannot be really take a shape of a cone, hence we need to make an approximation. And the approximation here is, instead of using one wire, what if we use 3 wires? Then at the top view it will look something like this, that there is a melt pool created and in this melt pool 3 wires are fed. Now obviously that if you move in any direction, approximately the scenario will remain consistent, meaning the angle between VF, VS and VD will be approximately same, and hence the process will become omnidirectional. But please note that it is not an accurate method, it is an approximation for method 2. However, if you use powder as a raw material, then it is possible to feed the powder in a conical form. But in the case of TIG or plasma cladding based DED systems, we really cannot use powder as a raw material. Preferably, if you make such kind of approximations, 3 wires are minimum required and they should be at 120 degree apart. If you do so, then definitely approximately the process will become omnidirectional. However, the method 3 can be easily implemented, and if we implement the method 3, we can say the wire should be coaxial, because powder we cannot use in tungsten, so I'm talking only about the wire as a raw material, and this wire should come from center and it should be surrounded by the fusion source in a conical form. So in that case, your tungsten electrode should be hollow and it should be in the form of a cone. Already some patents have been already filed. We have found very old patents already filed for hollow cathodes or for hollow electrodes where the wire is fed from the center in the TIG welding process. So the need is very simple to achieve the omnidirectionality. So if the wire is coming at the center in such a system, the tungsten which is hollow will create the arc, and the top view of the same will look something like this. This hollow tungsten will create hollow arc, and that will get merged at a particular point, and at the same point the wire will get fed into the molten pool created by the fusion source. In this case, this will be the vector orientation diagram, which shows VF will be always vertical, VS will be in the form of a cone, and VD will be on the XY plane. Now we move in any direction, in this direction or in any direction, the angle between VD, VF and VS will remain consistent, and hence the process has become omnidirectional. The similar kind of a patent was found for plasma as well. We know that there is not much difference in the case of plasma and TIG cladding based DED system. We already discussed it. In this case, again, there will be a hollow electrode, but it will not projected outside. It will remain a little bit inside into the nozzle, and the shield gas along with the plasma gas will create a hollow plasma, and that will provide the provision of feeding the wire from the center. The top view of the same will look something like this, where there will be a wire at the center surrounded by the fusion source, as you are seeing in this case. Again, in this case, very similar to TIG, the angle between VD, VF and VS will remain consistent throughout the process, and the process will become omnidirectional. The fourth method says that we can implement the dynamically adjusting feedstock or deposition direction. Now let me consider that there is a TIG welding which is having a tungsten electrode, and it is creating the arc like this, in which we are feeding wire from side. Now assume that the substrate is mounted on a rotary platform, and the vector orientation diagram will look something like this. Here the vertical green line is showing the vector corresponding to the fusion source. The red line is showing the vector corresponding to the wire feed, and VD is showing the vector corresponding to the deposition direction. Now in this case, what will happen if the direction VD will change? If VD will change, then the angle between VF and VD will change. Hence, we should maintain the angle between VF and VD to make the process omnidirectional. So what we can do, instead of changing VD, we can rotate the substrate in such a way that the VD will remain at the same position. As a result, the angle between VD and VF can be always same, and hence process will become omnidirectional. In a similar fashion, if you don't want to change the direction of VD dynamically, you can rotate the wire feeder as well. In that case, the system will look something like shown in this diagram. Here there is a wire feeder which is attached through the bearing onto the cladding torch, and when required, this wire feeder will rotate. In that case, you can see the vector diagram again, that there is a green vector corresponding to the fusion source and the red vector corresponding to the wire, and VD is the deposition direction. Now if the deposition direction will change, this VF will also rotate, and it will maintain the angle between VF and VD. The method of rotating the wire is called as omnidirectionality through the dynamic orientation of feedstock delivery, and rotating the substrate is called as omnidirectionality through the dynamic orientation of the workpiece. Both of the methods falls into the category of number 4. So let me show you the example for the both. Here you can see that the substrate is rotating, and as the substrate is rotating, you can notice now always the front feeding is maintained, right? Always the tungsten is creating an arc and wire is fed into the melt pool from the front, and all the time it remains front feeding. This particular method is corresponding to dynamically orienting the position of the workpiece. While on this particular video, you will see that the wire feeder will rotate around the torch in such a way that the angle between VD and the VF can remain always consistent and the process will become omnidirectional. Here you can see as the VD is changing, the wire feeder is also rotating in order to maintain the same angle, and this will be called as omnidirectionality through the dynamic orientation of the feedstock delivery. So let us now talk about the DED system where laser is used as an energy source. So generally for the wire form of feedstock, the method of its feed into the melt pool is similar to the one discussed for TIG and plasma based systems. However, when we use powder as a feedstock, especially dialed nozzles can be used for method 2, method 3 and method 4. So let us try to discuss, and we shall start with method number 2. So as per the method number 2, the fusion source will be coaxial and it will be surrounded by the feedstock. Now, like I already mentioned, as we are now having a freedom of using the powder as a raw stock material, we can form a proper cone like you are seeing here surrounding the laser beam coming coaxially through the center. If you draw the vector diagram of the same or this kind of system, then it will look something like this, where the VF vector is in the form of a cone, VS is coming at the center, which is shown here in the orange color, and now you can move in any direction which is represented by VD, and you can notice that the angle between VF, VD and VS will remain consistent. The top view of the same will look something like this. An approximation sometimes is also preferred, where instead of having a continuous nozzle, a discrete nozzle is used where multiple channels are given. Preferably, these channels are varying from number 3 to 6. Then the powder is coming from these channels and getting converged at a particular point. Now this scenario is similar which we discussed in the case of TIG or plasma welding, where wire was used, and as the wire cannot be used in the form of a cone, 3 wires were used. Those were at 120 degree apart and got feed towards the melt pool. Here also in a similar fashion, instead of wire, 3 nozzles are there, and these 3 nozzles are feeding the wire and which is getting converged at a point which is also called as the focal point. Now the top view of the same will look something like this. Here, as you can see, it is approximately forming a cone at the focal point, but I cannot call it as the material is fed in the form of a cone like in the continuous feedstock nozzles. In such case, the vector diagram will look something as shown here in this diagram, where VF is representing the direction of the material feed, and as 3 nozzles are there, that is why it is approximately forming a cone, and then VS is coming from the center, it's shown here in the orange color, and then you can move in any direction represented here by VD. Now it can notice that if you move in any direction on the XY plane, then the angle between VD, VF and VS will remain consistent, and hence the process will become omnidirectional. Now let us discuss about the method number 3, in which the feedstock should be coaxial and it should be surrounded by the fusion source. So the example of the coaxial feedstock surrounded by the fusion source is shown here in this diagram. As we are focusing right now on the powder based system, but the same setup or the similar setup can be utilized for wire feedstock as well. So as we are using a laser here, we have an advantage that if you use appropriate optics, you can really play around with the laser beam and able to obtain different shapes. Like here in this example, there is a conical shape laser beam. If you take cross section at any plane of this type of a laser beam, you will find a donut shape cross section. Now in this case, if I draw the vector diagram, it will look something like this, where the cone is representing the fusion source and represented by VS, and from the center the raw stock material is coming, and which is represented here by VF. And then you move in any direction VD on the plane, it can be noticed that the scenario will remain consistent, and hence the angle between VS, VF and VD will be same, and the process will become omnidirectional. Even though such a setup has been also shown the higher powder catchment efficiency, but generally are not really preferred due to the involvement of the complex optical system. Why catchment efficiency is improved? Typically the powder is completely entrapped by the fusion source if you look here in the top view, and the powder particles, even those are getting bounced back, may further, due to the availability of the laser source surrounding it, may melt the powder particle and hence deposit on the substrate. That's why the catchment efficiency in such systems are noted to be better than the conventional ones. But like I already mentioned, it is always not very easy to convert a solid laser beam to this type of a donut shaped laser beam cross section. It requires a very complicated optics, and that further required a complicated cooling of the optics to do the same thing. An approximation also sometimes is observed for the similar system, where instead of having a conical form of the laser beam, we can have multiple laser beams which can approximate the cone in a very similar fashion which we discussed earlier. Here now, instead of having the cone of the laser beam, 3 laser beams are shown, and they are at 120 degree apart, and from the center the powder feedstock is fed into the melt pool. If you draw the vector diagram of the same, it will look something like this, where VS is representing an approximate cone, VF is representing the feedstock material direction, and VD is representing the deposition direction. It can be noticed now, approximately if you move in any direction on the XY plane, the scenario will remain consistent, and hence the process will become omnidirectional. Let me now show you an example of method 3 when it is implemented with the laser beam. First, the laser beam is trifurcated into 3 laser beams by using appropriate optics, and then from the center the wire is fed, which is the material feedstock, and the process becomes omnidirectional. This type of laser system is quite popular for additive manufacturing, and now you know the reason. It is only because the process has become now omnidirectional. You move in any direction, the angle between VF, VS and VD remain consistent. In some of the literature, I have also observed, instead of using a single beam of laser and then trifurcating it by utilizing the appropriate optics, you can also utilize 3 laser beam source itself to get converged at a particular focal point, and from the center one can feed wire in that case as well. The method 4, which is dynamically adjusting the feedstock delivery or deposition direction, is quite similar what we discussed in the case of the TIG and plasma based system when wire is used as a raw material. But if the powder is used as a raw material, such a system is not really popular. It is because if you change dynamically the direction of the material feedstock, and if it is in the form of powder, it will fall here and there, and as a result your catchment efficiency will definitely reduce. This is because the rapid change in the feed direction, and it will more likely disrupt the powder streamline, and that will give like spray like pattern rather than converging at a particular point. And that is why the powders are not really preferred with dynamically adjusting the feedstock delivery or deposition direction. Although if the laser is used along with wire, then definitely this method 4 can be used appropriately if the wire is used as a raw material. Let us now discuss about the electron beam if it is used as a fusion source in the DED. Typically, a vacuum environment is required for successful material processing using electron beams. Since most of the powder feedstock handling systems uses pneumatic methods, wires are properly used as a feedstock in DED system where electron beam is used as a power source. So in order to achieve omnidirectionality in EB system, the method 2, method 3 and method 4 can be implemented, as we discussed, very similar to TIG or plasma based systems. So the method 2, which is saying the coaxial fusion source surrounded by the feedstock. If we are feeding the fusion source at the center and it has to be surrounded by the feedstock, I already mentioned that the feedstock can be only in the form of wire, then we have to only use its approximated method. According to that, the 3 wires will be fed towards the melt pool and these wires will be at 120 degree apart. So this is only because we are using wire as a raw material, but if someone is able to develop a powder delivery system for electron beam, I mean in the vacuum environment, then definitely the continuous cone or the discrete nozzle type of systems can also be used here to make the process omnidirectional if powder is used as a raw material. But it is not really found till now in the literature that popularly the powder is used in the vacuum environment where electron beam is used. If the method 3 is used, then the powder should be coaxial and it has to be surrounded by the fusion source. In such a case, assume that if you have this feedstock, which is the wire, of course we cannot use powder like I already mentioned, and then we have 3 electron beam guns. These 3 electron beam guns are rotating with a very high speed because electron beams are known for oscillating with a very high speed. They can do that, and as they can do, they can virtually form an annular beam kind of shape like you have just seen in the case of laser. And at the focal point you will see the top view something like this, where the single beam which is oscillating with a very high speed will form a cone here, another beam will form a cone here, and another beam will form a cone here, and each beam will cover 120 degree distance. Then it will entirely 360 will covered and you can feed the wire from the center. Now you can imagine that if VF is showing the vector corresponding to the wire feed, VS is showing the vector corresponding to the fusion source, and VD is the direction in which we are moving, then the scenario is consistent if you move on the XY plane, and the angle between VF, VD and VS will remain same. In another system which has been found that the hollow cathode is also preferably used. It has been observed in some of the commercial systems as well. So if the hollow cathode is used, it will emit the electrons, and the emission of electron will be in the form of a hollow beam. Now the beam itself is hollow, but as it is further passed through some focusing coil, it is going to get conversed. So it will be perfect conical shape as you are seeing in this diagram. As a result, if the VS is representing this cone, VS is representing the direction of the wire feed, and VD is representing the direction of the deposition, then if you move in any direction in the XY plane, the angle between VF, VS and VD will remain consistent and the process will become omnidirectional. You can also dynamically adjust the feedstock or deposition direction like Siaki does. As you can see here, there is a component which is rotating, and the rotation of this component is mainly to achieve the omnidirectionality only in the process. As in this case, the wire is fed from the side and the beam is creating a melt pool. A rotary table is typically used to rotate the part in such a way that a particular type of feeding mechanism can remain consistently maintained. It could be front feeding, back feeding or side feeding, but one of the type of feeding which is preferable is always maintained. Let us now discuss the omnidirectionality in material extrusion. So the extrusion based additive manufacturing process are typically identified by nozzle through which the material under pressure is forced out and deposited on the print bed. Fused deposition modeling is one of the most commonly used extrusion based additive manufacturing technology for polymer and plastics. FDM is generally assumed to be omnidirectional in nature, as the material is extruded through a circular orifice, resulting in uniform track dimensions. Now, in that case, in particular in the case of FDM, as the wire is getting melted and it is getting deposited always vertical to the deposition direction, you move in any direction, the direction of the VF, VD and VS will always consistent and the process are always omnidirectional. So FDM are typically omnidirectional in nature. But few extrusion based processes have found to be used the rectangular orifices for the nozzle instead of circular nozzles, and it is preferably due to appropriate stacking of layers. So in such cases, if we use circular nozzle, then there may be a chance of having void, but if you use rectangular nozzles, the stacking of the layers is quite good and there are less chance of getting the voids. But if we use the rectangular orifice, then there may be an issue that may arises and make the process non-omnidirectional. Let us consider it. Assume that you are using a nozzle which is having a rectangular opening. Now if you deposit back and forth in this direction, then the width of the deposited track will be equal to this dimension, which is assumed to be B of the opening of the orifice. But if you change the direction of deposition to this vertical direction, back and forth in this direction, then the deposited track width will be different and it will be equal to the dimension of the another edge of the rectangle of the opening of the orifice. Also, if you deposit diagonally, you can imagine that the dimension of the deposited track will be further different and it will be root over a square plus b square. So the point here is, now you are having a system, and if you are just changing the deposition direction, the width or the geometric properties of the deposited track will be different. And if you recall our definition, it says if a process is giving different mechanical or material or the geometrical properties while changing the direction of deposition of or the adding the material, then the process is not omnidirectional. Hence, the process has to be made omnidirectional by some appropriate manner. Also, another issue arises when we use the rectangular nozzles. If we take a turn, a twist is usually observed due to the sudden change in the direction of the deposition. So the solution for that is typically by method number 4, which we discussed, and it says we need to dynamically adjust the feedstock delivery direction. So assume that this is your nozzle and it is trying to deposit material along this path. Now to obtain the uniform width of the deposited track, you have to rotate your nozzle in such a way that it always follows the same pattern, meaning to say, if for example this particular edge, it should be always perpendicular to the direction of the motion, that may be VD. And in order to achieve that, you have to rotate your nozzle. So a real life example of the same is shown here in this video as well. As you can see, there is a nozzle which is continuously rotating when it's required to deposit the rectangular bead onto the substrate, and it is rotating, you know that now, to achieve the omnidirectionality. If this opening of the nozzle is circular, then this issue may not be here, but the solution, as the opening of the nozzle is rectangular, the solution is dynamically adjusting the feedstock delivery direction. Let us now discuss about the omnidirectionality in wet photopolymerization. So most stereolithography processes uses galvanometer to deflect the incoming laser beam onto the photoresin tank. Laser beam is striking the build surface at an inclination to the vertical, result an elliptical spot rather than circular one. We already know that. So if the laser beam is just falling at the center, it will give you perfect square cross section of the laser beam. But if it is deflected away, you can imagine very easily the projection of the laser beam onto the wet photopolymer bed will be elliptical in shape, and this size and shape of the ellipse will keep on changing on different location of the bed. I'll give you an example that an inclination of 45 degree reduces power density by 30% and increase interaction time by 40% at original travel speed. So the process becomes really inefficient in such a case. Also, the geometric properties which you are trying to achieve at center and at the corner or and other locations will not be same. You will get different size of the bead width in the center, but you will get different size of the bead width when you are striking your beam somewhere else apart from the center onto the wet photopolymer. And it is happening because we are using a galvanometer. The principle and how galvanometer works we have already discussed in module 2. So let us check for the omnidirectionality nature for this. We will apply our same rule and check for the 3 vectors only. So it can be noticed that in the wet photopolymerization based system we pre-place the liquid material, hence the VF means the vector corresponding to the material feedstock is going to be 0. But there are 2 vectors remaining. One is Vs, that is corresponding to the direction of the energy source or the fusion source, and another vector corresponding to the direction of motion or the travel direction given as Vd. The angle between Vs and Vd should remain same, but it is not the case. If I go back to this slide and show you, if the beam is striking at the center, the angle between the beam and the plane is 90 degree. But if you strike the beam at some angle, then the angle between the beam and plane will be some other angle, but not 90 degree. Now if you move in any direction, for example you are at the center and you are moving in this direction, the angle between Vd and the Vs will be 90 degree. And if you are projecting at another location and you are moving again, for example in this direction only, the angle will not be same between the laser beam and the direction of travel. Therefore, we are going to introduce another method here to achieve the omnidirectionality in such a system. And it is called as fusion source beam correction. And it is particularly for the galvanometric scanning system based systems. The galvanometric scanning systems restrict the motion of the laser beam to be having the same focal point in a spherical path. We already discussed it. Therefore, to obtain the same spot size onto the XY plane, we have to use some F theta lenses. And we have already discussed about it. If an appropriate optics is used, which I am calling here as F theta lenses, then the beam which is projecting on the F theta lens will strike down back onto the XY plane vertically. If the angle now between the Vs and the direction of motion, assume that in any direction in the XY plane is 90 degree throughout, then the process will become omnidirectional because now the angle between the Vs and the Vd is consistent. So the F theta lenses are the auxiliary arrangements in the wet photopolymerization based machines where galvanometer is used for scanning to achieve the omnidirectionality. It has also been found that we can use flying optics instead of having F theta lens. What is flying optics? In the case of flying optics, we have the laser beam, and instead of deflecting it by utilizing a mirror at a fixed position, we move the entire head of the laser beam and maintain the 90 degree angle between the laser beam and the liquid photopolymer or the bed of the liquid photopolymer. In such a case, now if you move in any direction in the XY plane of the wet photopolymer bed, the angle between the laser beam and the deposition direction will remain consistent, and that will be always 90 degree, and hence the process will become omnidirectional. One such system is shown here. This is the inverted system, and this one is when the flying optics is coming from the top and there is a liquid bed here. You can see that now laser beam is mounted on the XY table on the top side, and it is moving the laser beam and maintain the laser beam and the deposition direction angle always 90 degree, and the process is omnidirectional. So we have seen the method 5 for correcting the laser beam shape by utilizing the F theta lens. or by using the flying optics. Also, in method 5, to achieve the omnidirectionality, in particularly in the wet photopolymerization case, the DLP is used. The digital light processing or DLP based systems use digital mirror device. As you can see here, they are consisted of several micro mirrors, and when the floodlight falls onto it, the light is projected perpendicularly onto the wet photopolymer bed. As the light is projected perpendicularly now, the process becomes omnidirectional, like we discussed in the previous case as well. The similar scenario is observed when the mask is used. If the photo mask is used instead of DMD, then also it will not allow the light to pass through from some of the portion wherever it's not required, and it will allow the light to pass through only from the region where it is required. From where the light will pass through, it will strike to the wet photopolymer bed perpendicularly, and hence you will obtain the omnidirectionality for the system. So let us now discuss about the omnidirectionality in sheet lamination. So let us first check for the sheet based system the inherent omnidirectionality nature. The sheet lamination is an additive manufacturing process that employs pre-placed feed stock. So if the feed stock is pre-placed, we can simply eliminate one of our vector, that is VF. VF is going to be 0. So we are going to worry about only two vectors, VS and VD. Also, but we need to remember here that additional process is typically utilized in the case of sheet based process, and that is the cutting operation. Without cutting operation, no sheet based process may work, because otherwise if you just stack only the rectangular sheets one over another, you will end up making only rectangles. So cutting has to be there. So it may be possible that that cutting operation is not omnidirectional if even the deposition process is omnidirectional. So for example, in the case of powder feed stock, the layer geometry is carved out either by mechanical knife or by laser. And in the case of metal, an iron milling cutter is used to carve the layers to join together, like for example in the case of ultrasonic consolidation. The energy source also is typically vary in different sheet based systems, like in the case of metals it is ultrasonic vibration or friction heating, or the solid state joining like friction stir welding. And in the case of the paper or sheet based process, either it is thermal activated glue or pressure activated glue. So let us talk about FSW. It is a well known process where there is a tool which is going to join the two sheets together, and these two sheets are lying like this, as you are seeing in this diagram. If the tool is always perpendicular to the sheet which it is trying to join with the substrate or pre-built layer, then definitely the angle between the deposition direction or the material addition direction and the source of energy, that is vertical, is always having the 90-degree angle, and it will remain omnidirectional. But if you are giving an angle between VD and the for example FSW tool, then the process will not remain omnidirectional, and if you change the direction VD, then the angle tilt direction will change and you may not obtain the same property. But typically in most of the systems, the angle between the fusion source and the deposition direction is 90 degree. But there is an issue for omnidirectionality for cutting the material. So let us discuss about the metal based system for cutting as well. So typically after joining the two sheets of metal, a hand milling cutter is used to cut the remaining portion. And as hand milling cutter is always perpendicular and it can move in any direction without an issue, process is omnidirectional. But for the case of paper cutting, if you remember the laminated object manufacturing process, we use a laser beam to cut the remaining portion of the sheet. In that case, typically the laser beam is moved through a galvanometer, and if the laser beam is striking on the galvanometer, we have just discussed, and we are projecting it away, not exactly under the galvanometer, where the angle between the fusion source and the sheet of the paper will be not 90°, in such a case we will have some issues. In such a case, definitely you will require some additional systems to make the process omnidirectional. Either we use method number 5 here now by utilizing the F-theta lens, or by utilizing a flying optics to cut the paper to make the process omnidirectional. Also, in some systems like Kiraz loam, we have discussed that a knife is used to cut the material. Knife itself is not a omnidirectional tool, because you know that the knife can cut only in one direction. It cannot cut in any direction. You cannot just move the knife in another direction to cut the material. No, it's not possible. Hence, you have to change its orientation. Therefore, method number 4, if you recall, dynamically adjusting the cutting edge orientation for cutting direction should be used. So if you are cutting in this direction, then the knife will be aligned like this. But if the direction of the cutting is changing, then your knife has to be rotated appropriately to cut the sheet. So this auxiliary arrangement is nothing but to make the process omnidirectional. But it can be noticed in majority of the laminated object manufacturing, the omnidirectionality is required for cutting the material, not for adding the material. Typically the adding process are omnidirectional in nature, but the cutting processes are not really. We have just seen 2 examples. So if the energy beam is used to cut the paper, like I already mentioned in the case of laminated object manufacturing, then let us call it as method number 6. We have to use either F-theta lens, or we have to use flying optics, as we just discussed earlier. Let us discuss about now the omnidirectionality in powder bed fusion. So in several aspects, powder bed fusion is very similar to wet photopolymerization. For example, both utilize the pre-placed feedstock. In the wet photopolymerization, you pre-place the liquid material. Here you pre-place the powder material, and then a laser beam is used to scan the desired region. So as the material is pre-placed, of course in this case VF will be 0. Hence we need to be worried only about VS and VD. And if VS and VD are not always perpendicular, the process is not going to be inherently omnidirectional. Hence we have to correct the beam shape, and for that we have just discussed 2 methods in 5A and 5B, and that says either we use F-theta lens like you are seeing here, and in most of the powder bed fusion system typically F-theta lens is used to correct the beam shape, and what it does, it basically maintains the angle between the fusion source and the deposition direction VD. It always remains 90° then. It is very important to use the or to make the process omnidirectional in such a case, because in many studies it has been found that the dimensional inaccuracy occurs up to as much as up to 21% as compared to the part when it is built on the center. Also, in some of the literature, it has been found that instead of using the F-theta lens, a flying optics is used, and we have already discussed that in the case of flying optics, your laser beam will always remain perpendicular to the powder bed. But here there will be a compromisation, and that compromisation will be on the speed of the laser beam, because you can't really now move with a very high speed if you are using flying optics. The next is omnidirectionality in material jetting. Most material jetting systems use feedstock in the form of powder or liquid droplets, and they are delivered to the build area through a nozzle. And if you notice, each time these nozzles are always perpendicular to the substrate or the pre-built part. Therefore, the direction of the material delivery, that is VF, and the direction of the motion is always perpendicular, and the fusion source is always stationary in such cases. So the condition for inherently omnidirectional is quite satisfied in most of the material jetting based additive manufacturing processes. Therefore, these processes can be considered typically omnidirectional in nature. But if you are coming up with an idea of injecting the material at an angle towards a point onto the substrate, then you need to consider some methodology of making the process omnidirectional. So let us now discuss the last process, that is the omnidirectionality in binder jetting. Similar to material jetting, in the case of binder jetting, additive manufacturing are also inherently omnidirectional. In the case of binder jetting based process, we know that there is a nozzle which injects the binder onto the pre-placed powder, and each time the nozzle is always perpendicular to the bed of the powder bed. As it is always perpendicular, the angle between the travel direction and the fusion source will be always 90 degree, and already VF is 0 because you are using the powder bed which is having pre-placed powder. And as the angle between the VS and VD is going to be 90 degree throughout the process will be inherently omnidirectional. So with this, let me conclude this presentation. Omnidirectionality implies invariance in the material and geometric properties of as-built parts across various AM platforms. The processes of binder jetting and material jetting are found to be inherently omnidirectional. Other processes, however, require additional consideration to be called as omnidirectional. The use of Theta lenses, layer irradiation, the flying optics are suitable for achieving omnidirectionality in wet photopolymerization. Powder bed fusion, which is similar to wet photopolymerization in the context of omnidirectionality, employs Theta lenses and flying optics. FDM is typically omnidirectional, it has been found, but if the rectangular nozzles are used, like in the case of concrete printing, the constraints are there and we have to ensure the method of dynamically adjusting the feedstock delivery direction to achieve the omnidirectionality. And now the last but very important, majority of DED processes are non-omnidirectional. Apart from the big base process, the metal inert gas based wire arc additive manufacturing process, all the other processes are inherently non-omnidirectional. And they typically rely on the achieving the concentricity of the powder feedstock and fusion source to establish the omnidirectionality. Hence, in DED based systems, some additional arrangements are always found to achieve the omnidirectionality. So this was all about the omnidirectionality in additive manufacturing systems. Thank you very much.